Okay. Okay, and I should mention, if you have a question that you want to ask during the talk, you should feel free to ask it. Okay, I'll try to notice you if you ask a question, but if I don't notice you, you should raise your hand and say, I have a question or something like that, and then we can try to address it. Okay, so what I did in the first part of the talk was to talk about some of the underlying fundamentals, right, that go into plasmonic phenomena, how you try to exploit light scattering, and so forth. So what I want to do in the second part of the talk, okay, is to look at a couple examples of how we and others are trying to use these ideas. So one example that we'll look at just somewhat briefly is the use of these ideas in thin film amorphous silicon solar cells. And then we'll look in more detail at how some of these ideas can come into play in concepts for high efficiency 3-5 heterostructure solar cells, quantum well structures as well. And then I'll say a little bit at the end about how you can use control over photon propagation to increase voltage rather than, or perhaps in addition to, current. Okay, then we'll summarize. Okay, so we have these two examples that we want to look at, right? The amorphous silicon example, right? That's basically this situation over here, right? You have a material that has a lot of defects. The minority carrier diffusion and carrier transport lengths are not that large, they're not that long, right? So the devices are typically quite thin, maybe on the order of a few hundred nanometers, right? Because of these limitations. And that is not enough to give you complete absorption at long wavelengths, right? So can you use these kinds of effects to improve, particularly the long wavelength absorption, right, in that type of device? And then the other example that we'll look at in more detail is essentially something along the lines of this over here, where in the particular case that we'll look at, you have quantum well structures that are embedded within your solar cell to enable you to have longer wavelength absorption, hopefully with minimal hit in the voltage, right? And you want to try to take advantage of light trapping effects, photon control over the photon propagation, to increase the long wavelength absorption in thin layers of these structures over here. Right, so that's what we want to look at. So if we look first at amorphous silicon, okay, this is something that we actually did some work on, again, quite a few years ago, looking at amorphous silicon thin film solar cells. You put, at that time, particles on the top, and you get an increase in short circuit current and power output, sort of on the order of several percent. All right. So this has been looked at in quite a bit more detail now by a number of groups. I show one example of this over here, right, where in this case, what's been done is to take a substrate that is patterned, right? So you create sort of regular topography on this, and then you deposit, these then act as scattering elements, right? Then you deposit amorphous silicon on that patterned surface, okay? And you look at the IB response. And what you see is that compared to just a flat amorphous silicon solar cell, which is this green curve over here, if you have roughness with different periodicities, or in the case, this is just doing this on randomly textured, commercially available SI glass, right? Then you see a substantial increase in the current, okay, and therefore in the efficiency, right? But the amount by which it increases actually depends quite a bit on the nature of topography that you introduce, all right? So for different periods, right, 500 nanometers is the blue pitch, 700 nanometer pitch is the red, right? They're actually quite different. And then the randomly textured Asahi glass is sort of in the middle here, all right? And we can understand what's happening here in this work using the ideas that I described in the first part of the talk, having to do with these periodic scatterers, okay, and coupling to specific guided nodes that is enabled by various reciprocal lattice vectors of the periodic structure over here. Okay, and so that's what actually is shown in these images here from this publication, all right? This is the external quantum efficiency as a function of wavelength and angle of incidence for light incident on a solar cell that's on this randomly textured glass, right? And you see actually there's very little dependence on the angle, because for any given angle at a given wavelength, since you have random texture, you'll have some Fourier component in that texture that allows you to couple into some guided mode. All right? And then so you don't really have that much dependence. If you look at a periodically patterned structure, you see there's much more structure to this. Okay? And what is happening here is that, excuse me, for a given angle of incidence and a given wavelength, okay, at certain wavelengths, there will be some reciprocal lattice vector that's associated with this patterned periodic structure that allows you to couple into one of the guided modes of your thin film structure, right? But at other wavelengths, there isn't, right? And these will have a dependence on angle and wavelength that you can calculate and understand, and in fact, you see that in the experimental measurements over here, right? So there's a lot of, and then you know what I showed in the first part was essentially a cut through this at normal incidence, right? So the main idea to take away from this is that you know, even in something that's pretty well established like amorphous silicon, you can use these kinds of effects to get significant improvements in this case, current, all right, and therefore efficiency. But the details of this matter. If you want to do the best possible job of this, you really have to think about you know, what kind of pattern structure do you want, and what its effect is going to be integrated over wavelength, over the range of wavelengths that will be incompletely absorbed. Right? And then if you're trying to sell these things, you have to think about whether it's expensive to do this and so forth as well. But we're concerned here with mostly understanding just the physics as a first step. Right? So this example is fairly simple, just for amorphous silicon. Okay. What we'll spend most of the rest of the time on, all right, is we'll look at another type of device structure, a quantum Wall solar cell, where you have the potential to have very high efficiency, all right, but where you need to really resolve a fundamental conflict between what's required for efficient absorption and efficient carrier collection in order to realize high efficiency. And we'll look at how you can use some of these light trapping effects to try to do that. All right. So the basic idea in quantum Wall solar cells is as follows. Right? If you have say a PN homojunction cell, gallium arsenide, for example, then as I described early in the first talk, right, you have a certain flux of photons that you can absorb. You'll get a certain amount of energy out of each absorbed photon, and you'll get a power corresponding to the area of this green box here. Now, in a quantum Wall solar cell, right, what I've shown here is gallium arsenide with, you may not quite be able to see it, but it's Indian gallium arsenide quantum walls that are embedded at the junction. The idea here is that you want to use the quantum walls to allow you to absorb longer wavelength photons, right? So you have a larger photon flux available for absorption, all right? But then you try to design the structure so that the voltage at which you extract the resulting photogenerated carriers corresponds more to the band gap of the surrounding material rather than of the quantum walls. Again, it's actually very tricky to do this, but if you're able to do that, then essentially it allows you to get outside this inner curve over here so that you have a higher efficiency than can be realized with any single PN homojunction structure. All right? So this idea has been around for a long time, and there have been many studies of the theoretical limits to the efficiency, the power conversion efficiency that you can have with these and other related types of ideas. And depending on exactly how that calculation is done, you get numbers that are in the range of about 45% to, with some probably quite optimistic assumptions, greater than 60%. The corresponding values for this type of structure are 31% and 37%. All right. So it seems that there is the prospect to be able to get substantially higher efficiencies, okay, than you can get with a single PN homojunction. And from an applications perspective, this is potentially quite interesting because your device structure still has just a single PN junction. Right? So if you compare something like this to multi-junction tandem solar cells, right, which already give us very high efficiency, then what happens in those structures is that you reduce the cumulative thermal losses by having multiple band gaps, but you have multiple PN junctions that are connected in series. Right? So the current through all of them, since they're connected in series, has to be the same. All right? This is called the current matching constraint. And so you design the device so that for a given spectrum of incident solar illumination, you have the same photocurrent generated in each cell. and then it operates at its maximum efficiency. But if you have a variation in the spectrum, then the currents will no longer be matched, and what you end up getting out is actually the lowest of the currents. All right? And so if you predominantly lose absorption from one of the cells, then to the extent that that limits the total current, then it can very substantially degrade the efficiency. And this can be important in terrestrial applications because in terrestrial applications you have atmospheric scattering, which occurs predominantly at short wavelengths, right? It's rarely scattered, so it's 1 over lambda to the 4th. So you predominantly lose the short wavelength photons. And we know intuitively this is true, well, maybe not intuitively, but by observation you can know this is true because you look at the color of the sky. When sunlight is traveling through a large length of atmosphere, it looks red, right? You're losing the shorter wavelength photons. If you look at the scattered photons in the rest of the sky, it's blue, right? So in situations where you have this kind of spectral variation, there may be advantages to having a structure that can give you high efficiency with just a single PN junction. Right? Now, as I said, this idea has been around for a long time, but it's been very challenging to actually realize the very high efficiencies that have been predicted for these types of structures. There are a variety of reasons for this. One set of reasons has to do with basically materials issues. You have to minimize interface recombination at the quantum wells, you have critical thickness constraints, and so forth. But then more fundamentally, you have a conflict between what's required for efficient absorption at long wavelengths that are absorbed only in the quantum wells, and efficient extraction and collection of the photogenerated carriers. Okay. And the way this shows up in these types of devices is as follows. Right? So you have light coming in this way, right? And you have a typically multiple quantum well structure in here. If you want to have complete absorption of the long wavelength photons that are only absorbed in these layers, then what you need to do is you need to basically have a thick multiple quantum well stack, right? On the order of probably a micron or more in thickness. However, if you want to collect the carriers that are generated in the quantum wells, it turns out for various reasons to be very helpful to have a thin multiple quantum well layer, more like, say, 0.2 to 0.3 microns. All right? Now these are non-overlapping ranges. Okay, so there's a fundamental conflict that comes into play between what's required for efficient absorption and efficient carrier collection. But you need both of these to be efficient to have a good solar cell, right? So how do we resolve this? There are a variety of ways one can think about doing this. What we've done is essentially to accept that if you want to collect the carriers, you're kind of stuck with having a thin multiple quantum well layer. All right. So then you can ask a somewhat simpler question, which is how do you improve the absorption efficiency in this thin multiple quantum well layer? Right. And given what we've been talking about for the last hour or so, right, the answer should be obvious. Okay, you use these light trapping approaches. So in trying to do this, there was one approach that we tried initially, which worked, but not that well. But the reason it didn't work that well is instructive. Right? What we did initially was to look at structures like this and recognize that in the quantum well regions, right, they have a smaller band gap, right, and that is accompanied by having a larger refractive index. Okay, so this idea is well known in, for example, the semiconductor laser community. It's used for guiding of laser moons. Right? So we can use the same idea here to recognize that, in fact, there will be lateral propagation modes that are confined by this refractive index contrast over here. All right? And so then you can put, say, scatterers on the top surface, and you can couple light into these modes and increase absorption in multiple quantum well regions. Right? And in fact, that does happen. Right? You can see experimentally that that does happen. But that process is not very efficient. And the reason it's not very efficient is that the contrast in refractive index between this region here and this very thick gallium arsenide substrate below it is not that large. It's maybe 0.1 or so, right, would be a typical value. So you actually have a lot of substrate radiation modes, and a lot of the light that's scattered doesn't go into this kind of mode, it goes into a substrate radiation mode, right? Which, it's not bad, but it doesn't really help you either. Okay, so what we've been doing more recently is to look at structures like this, where you remove your active device regions from this thick substrate, right? So that your entire device, which is maybe, say on the order of half a micron to a few microns in thickness, right? That's your entire device. it's removed from the substrate, so you can put scattering elements on the backside, right? And then you have light coming in. The short wavelength light can get absorbed on the first or maybe a few passes by reflection through. And you optimize this structure down here so that it efficiently scatters the long wavelength light that is absorbed only in the quantum walls into these guided modes, right? So that the light is propagating this way, and it has a much better chance of being absorbed in these regions over here. Okay, so that's the basic idea. So what are the things that you need to do in order to actually realize this? There are a whole bunch of things that you have to pull together, right, to do something like this. The basic idea, right, as I've illustrated here, is that you have, say, generically some thin film solar cell, right? So this can be applied to a variety of types of devices. What we're talking about here is a specific implementation of this for quantum solar cells, but it could be any thin film solar cell where you need increased absorption over some range of wavelengths. All right? For the quantum solar cells, there are issues that you have to work out with epitaxial growth of these structures, understanding material constraints, carrier transport, and so forth, in the overall design of this device. You need to implement a process for separating this device from its growth substrate, but there are established ways for doing this, so it's really implementing rather than developing. And then you have to think about the design of these scattering structures that you have on the backside combined with the overall structure of this device, such that you efficiently couple incident light at the longer wavelengths into guided modes, right? And so you do numerical simulations to try to get that to occur, all right? So these are kind of the different pieces that you have to bring together in order to do this. And what I'll try to do is to talk about several of these in turn. Okay, now there's also an issue that you have to worry about that has to do with the nature of optical absorption in quantum loops. Okay, and it's important because if you have a semiconductor quantum wall structure, the absorption actually depends on the polarization, the direction of the electric field. Okay, what happens is that the absorption for certain states, okay, say heavy hole to conduction band states versus light hole to conduction band transitions. For the heavy hole transitions, you have certain polarizations for which that transition is forbidden. Okay, and that's important, in particular when the electric field is in the vertical direction, right? Then that transition may not occur, or it may be. Now, this is important because if you have light that's coming in and propagating in this direction here, right? Then the electric field, right, it's always going to be perpendicular to the direction of propagation. So it's always going to be in the plane of the quantum wall, right? So parallel to the quantum wall. And so that'll give you one absorption spectrum, right? But if the light is scattered into a lateral propagation mode, right, the light is propagating this way, so the electric field, right, could have components that are either parallel to the junction, or to the quantum walls, or perpendicular. And the absorption will be different for those cases. Right, so if you're concerned about absorption for photons that are traveling this way, you have to work out and incorporate this polarization dependence of the quantum wall absorption. Okay. Now it's known how to do this, so we just have to incorporate this. And the way we do that using this kind of expression here. And again, I'll just sort of say what each of these terms corresponds to. There's a term over, this is the absorption coefficient, right? There's a term in this that corresponds to basically the momentum matrix element, between the optical transition element between the conduction band and valence band states. Right? That's essentially a bulk semiconductor property. You have a term over here that embodies these selection rules and the relative oscillator strengths and so forth. That gives you the polarization dependence. You have a term here that corresponds to the overlap integrals between the conduction band envelope function and the valence band envelope function. And then you have the quantum wall joint density of states, and a term over here that allows you to account for excitonic transitions and the like. Okay, so you put all this together, you get a polarization-dependent absorption coefficient that you plug into your simulation and use it. Then there's a question of how do you think about the design of these scattering structures down here? Okay, remember we looked earlier at sort of random distributions of scatterers versus periodic distributions, right? So do you want something that's random, periodic, or maybe something more complicated, right? We saw in the first part of the talk that when you have these periodic arrangements, right, you can get large increases in photocurrent response over narrower ranges of wavelengths. In this case, about 100 nanometers in wavelength. But if you have a thicker semiconductor region, you have more guided modes that you can couple into, so you can extend that. All right? And in this type of structure here, what we're mostly trying to do is to increase absorption at wavelengths where you have only absorption in the quantum lengths. And so that's maybe up to a few hundred nanometers in bandwidth. So you can probably engineer structures with periodic scatterers that will do a good job of this. Okay, so that's a reasonable starting point. So once you have that, then what you do is you do simulations, right, of a semiconductor device structure here. In this case, it's about 3/4 of a micron thick. And you have metal and dielectric scattering structures on the backside along with an anti-reflection coating on top. All right, in this case, it's palladium, I know it's hard to see, and silicon dioxide. And you vary the dimensions of these structures here until you maximize the absorption and therefore the expected photocurrent response. Okay, these are the values that you get for the different dimensions. Okay, now the specific values here are not important, and in fact they're not unique. Right, there are many different combinations that will give you about the same results. The thing to note here is that the period of this structure down here is on the order of a micron. All right. And the characteristic feature sizes range from, roughly speaking, about 100 nanometers to, say, roughly 500 nanometers. Okay, so those are the characteristic sizes of the structures that you have to make in order to get this, this idea to work. And then if you have structures like this, but these are not unique, right? And if you have structures like this, then you can get, at certain wavelengths, very efficient coupling into these well-defined guided modes. So then what you want to do is you want to see, okay, if you have a structure like this that has these scattering elements on the backside, and you compare the expected absorption in this kind of structure to what you would get if you just had a planar back metal contact of the same metal, right? Then how much better can you do, right? We also have this polarization-dependent dielectric function that we've incorporated. And what's plotted over here is the ratio of the absorption integrated over the volume of the semiconductor for the structure with these scattering elements on the backside compared to a structure that just has a planar back metal contact. All right? And that's this red curve over here and over here. And so we see three different behaviors here. All right? At the shortest wavelength, they're the same. All right? And the reason they're the same is because at the short wavelengths, the light gets absorbed on the first or maybe the second pass through. Right? The absorption coefficient is high. So, so you have the same result in either case. Over here, you have these oscillations. Okay, the reason this occurs is because you can have, when you have light coming in, when it's reflected off the back surface, it can get re-reflected at the top, and you can have Fabry-Perot resonances in the dielectric region here, the semiconductor. All right? So with a planar back metal contact, the thickness of the dielectric region is just the thickness of the semiconductor, essentially. All right? When you have this type of structure on the backside, you have some silicon dioxide in here, so that effectively makes the dielectric thickness look a little larger. And so the Fabry-Perot resonances will be shifted in wavelength, and you get these interference fringes over here. All right? So that's why you get this. These wavelengths over here then are the wavelengths that are absorbed only in the quantum lengths. All right? And what you see is that you can get, at a particular wavelength in this case, a very large increase in the absorption by a factor approaching 70. Right? So this, in this case, is larger than the 4n² limit, and fairly substantial increases over a broad range of wavelengths. Okay. But then, as we'll see later, what you really need is not only increasing by a large factor, but increasing to a reasonable absolute absorption efficiency. Right? If it's 0.01% to begin with, and you increase it to 1%, it's a factor of 100, but it hasn't helped you, or it's helped you very negligibly. Okay, so that was all simulation. But does this actually work when you do an experiment? Okay, so to see if it actually works, we can look at a series of epitaxial layer structures grown by MBE. All right, we have essentially three different variations. One of them being just a plain gallium arsenide solar cell, somewhat thin, but basically a gallium arsenide solar cell. And then we have a version that's identical, except that you've incorporated 12% ES quantum walls, okay, in here. And then a third version where, in addition to the quantum walls, you have some self-assembled quantum dots embedded in here to try to further extend the range of wavelengths that's absorbed. Okay, and then you grow these on a thick aluminum gallium arsenide etch stop layer that you use in the process to remove the active device layers from their epitaxial growth substrate. Okay, so the substrate removal process, I won't go through the details of that, but it's something that is pretty well established in the literature. What I've shown here is a cartoon and cross-sectional SEM images of what the device looks like after substrate removal. Right, so you have just your semiconductor active regions over here. They're metal bonded to a mechanical support, which in this case is a silicon wafer. And if you look at a cross-section of this in an SEM, you can see the metal layers over here. I know with the lights on, it's probably not that easy to see. And then the semiconductor regions over here, the thicknesses are pretty much what you'd expect. All right. Okay, yeah. So structurally, you can make these structures. All right. You can then take these and this is an optical micrograph of one of the devices that we made from this. Typically, for these experiments, we made devices that were either 1 millimeter or 2 millimeters on the side, fabricate top contacts but not anti-reflection coatings. And we just tested diode characteristics, and they look reasonable. Right, so you can actually take this process, you can make a reasonable p-n junction diode and photovoltaic device out of it. You can also look at the photocurrent response spectra. Okay, so the gray curve here is what you have from a device that just has gallium arsenide. The blue curve is for a device that has the quantum well layers embedded. And then the red curve is for the structure that, in addition, has these quantum dots embedded. And what you see is that, in fact, the quantum well and quantum dot structures do extend the photocurrent response to longer wavelengths, all right? Longer for the quantum dots than for the quantum wells. And in the case of the quantum dots, it's sort of moderately interesting to see that you have this long tail over here, which ends up coming from the size dispersion in the quantum dots that you form through the epitaxial growth process. Okay. But if you look at this, right, what you can see is that the efficiency of absorption that you have out here is low. Right? It's much lower than what you have back here. Right? So what you want then is, and the reason it's low in this case is because we have not, in these structures, implemented these light trapping and scattering approaches. Right? It's just a planar back metal contact. So what you want then is to use these light trapping approaches and scattering to bring this up, right? So that you actually get a larger contribution to the total current. So that's what's shown over here, all right? It's basically the same sort of device, except that on what ends up being the back side of the device, you fabricate these scattering structures. This is a plan view of the scattering structures, not a cross-section, okay? And then you measure the photocurrent response in devices that have these structures patterned on the backside versus those with planar back metal contact. And again, you plot the ratio. Okay, the blue curves here are what you have experimentally. The red curves are the simulations. Right? And what you see is that you see the same basic behaviors, right? The Fabry-Perot interference fringes over here. And then at the wavelengths that are absorbed only in the quantum wells, right, you see generically the same sorts of features, right? Certain ranges of wavelength where you get a fairly large increase in absorption, right? And then in regions where where the increase is smaller, right? They don't exactly overlap because the wavelengths at which these occur are very sensitive to the exact dimensions, and what we fabricate is not exactly the same as what's designed or simulated. But you see generically the same sorts of features and roughly the same magnitude of increase in the absorption. Right? Okay, so it seems like experimentally these ideas work, right? And then the question is, well, what is the best that you can do, or how well can you do with these kinds of approaches in getting high absolute absorption efficiency, particularly if you're constrained to have thin multiple quantum well stacks that are required to efficiently extract the carriers. Okay, so to illustrate some of the factors that come into play here, right, we can look at this diagram here, right? So what we have here now is one of these quantum well solar cell structures in cartoon form, right? These structures and simulations corresponding to this, these have somewhat thicker semiconductor layers, more like 2 to 2.5 microns. All right? That ends up being favorable because you have more modes that you can couple into, right, when it's thicker. All right? So there's a question of, if you have a small number of multiple quantum layers, then the single pass absorption efficiency is going to be quite low. All right? How well can you do in increasing the absolute absorption efficiency in such a thin layer, right, through these kinds of approaches? And how much absorption can you really get when you integrate over the full range of wavelengths that are absorbed only by the quantum ones? Right? And then you have issues like the following. Right? This multiple quantum well region is really quite a small fraction of the total device structure. All right? And if you look at the field distributions for these different modes, right, you can see that for each of these modes you have peaks in the field intensity, and then you have minimum, right, where the field intensity is actually very small. So it might end up that just by bad luck, right, you put your quantum wells in a region where at a node of the particular mode, or of some of the modes that you're trying to couple into, and then it probably doesn't help you at all, right, may even be detrimental. So you have to think about, okay, how do you position this layer over here, the multiple quantum layer, such that it has maximal overlap with all the modes that you're coupling into, and how does that couple into the overall design of the device and so forth. So there are a lot of things that you really have to think about together, right? So, so if you do all this, all right, then as at least a starting point to see, okay, how well might you be able to do, what I've shown here are simulations of what we expect the external quantum efficiency to be, assuming that we're collecting the photogenerated carriers from all absorption processes. All right? So that would be the best that you can do. For gallium arsenide homojunction cells in red, and then in green for quantum well structures for 10% indium gallium arsenide, 20%, and 30%, okay, with backside scattering structures consisting of palladium, which makes a reasonable ohmic contact to gallium arsenide, and silicon dioxide. Right? And what you see is that as you go to deeper quantum wells, right, you extend the wavelength range of absorption, and in this case here, 30% indium gallium arsenide, you can get, with a small number of quantum wells, this was either 4 or 6, you can get a peak absorption efficiency that's, in this case, over 40%. Right? So that's actually quite good. The average is maybe on the order of, say, 15 to 20% averaged over all these wavelengths. So that's still not bad. That can actually make a substantial contribution to the total current. All right? Now, is this the best that you can do? Actually, it's not, for a variety of reasons. One of the reasons is that there's this issue of metal absorption loss. Right? Palladium, even though it makes a good ohmic contact, is a very lossy metal. Right? So you could potentially do better if you used a less lossy metal, like gold, or the best case probably would be silver. Right? And then maybe you have a little bit of palladium to allow you to have a reasonable contact. So if you do the same simulation with gold replacing the palladium, you get these blue curves. All right, so you can see that actually the absorption efficiency has been substantially increased, right, up to, in this case, a peak that's approaching 70%, right, in a very small number of quantum wells, and an average over this range of wavelengths that's maybe 25 to 30%, right? And in this structure here, if you calculate the increase that you would get in, say, the short circuit current density, it's in the range of 15 to 20%, which is actually a large increase, right? In a structure that has a small number of quantum wells, such that you would expect to be able to have, hopefully, a minimal reduction in the open circuit voltage. All right? So, so these structures are hopefully being grown as we speak, and we'll see whether they end up giving us the results as promised. Now, what I've talked about, this is almost the end, what I've talked about for the most part up to here is using these kinds of techniques to increase optical absorption and consequently photocurrent response and then current in a photovoltaic device. All right? But are there ways in which these kinds of approaches can also increase the voltage? Right? And it turns out that not exactly these techniques, but things of along these lines actually can end up increasing the voltage as well. And this is something which there's been sort of renewed interest over the last year or two. And this occurs due to an effect that's referred to as photon recycling. All right? The basic idea is as follows, right? We have this picture over here that I showed earlier of different processes that occur in a solar cell, absorption, emission of carriers, and so forth. This is just another way of showing essentially the same processes plus one additional, right? So we have absorption of photons and collection of the carriers, right? That's basically this process over here in this cartoon. And then we have emission, recombination and emission of photons out of the device. That's this process over here, all right? But then when you have recombination and emission of a photon, it's not necessarily the case that that will escape from the semiconductor, right? It could be, in fact, very often it'll be that that photon is reabsorbed, okay? And then you have another chance to try to collect those carriers, right? And so this is referred to as photon recycling. People started thinking about this, back in the 50s. And it ends up allowing you effectively to have an increased radiative recombination lifetime, or essentially at a given bias voltage, you have a reduction in the external luminescence, okay? So you can get to a larger bias voltage with the same external luminescence that you're required to have by detailed balance, and that then allows you to operate your device when you have these photon recycling effects taken into account. It allows you to operate at a larger bias voltage, okay? And so I show a modeling result that shows this over here from a paper here in the 90s, all right? And there's been a lot of interest, but to do this, you have to make a structure that looks like this. It's a thin device. It doesn't have its growth substrate, and it has a reflector on the backside. So quite recently, within the last year and a half, something like that, there have been some results from a startup company, Alta Devices, where they've been able to implement this process and are attempting to scale it up to large areas. And they were able to show that due to an increase in the open circuit voltage that you get through these photon recycling effects, they were able to get to a record efficiency for gallium arsenide solar cells. Okay. So even though most of what I talked about had to do with increasing absorption and current, okay, which is very important, there are also ways in which you can use these kinds of effects and perhaps related effects to increase the voltage. And these are somewhat less explored, but very interesting as well. Okay, so to summarize, all right, the main points then are that you can use these methods for controlling photon propagation and exploiting plasmonic effects to increase absorption in some limited volume, thereby increase current. You have these two effects that you can try to exploit. Field localization due to plasmonic excitations and scattering effects by a variety of structures. And there are all these trade-offs that you have to think about. Do you want a large enhancement factor or a high absolute efficiency? Really, you want this. Having a high peak increase in absorption versus integrated over wavelength, what you need is this. Making sure that you take into account the effects of absorption losses in the metal. Optimizing simultaneously optical absorption and carrier transport. And then at some point thinking about the trade-offs between improved performance versus the process complexity costs and so forth. And then we tried to kind of look at these ideas in the context of two examples. Amorphous silicon thin film solar cells and these quantum hole solar cells. And then finally, looking at this idea of engineering photon recycling effects to increase the voltage. And then finally, and perhaps most importantly, these are the people who actually got all the results that I showed. So these are people from my group over the period that we've been working on this who worked on the things that I described. Actually, Daniel Schott should also be over here. He's now a professor in Germany. So we've worked with his group in Germany on some of this, with collaborators that we had at UC San Diego, and then also at JP. These are the organizations that paid some of those. So that's it.
Yes? thank you. It was quite interesting. So in the case of those quantum dot in well solar cell, can you please a little elaborate what is the difference between quantum wells and these quantum dot in well structures?
So the quantum dot structures are, and you've heard a lot about quantum dots, I think even in the last day or two, and then probably over the course of the workshop. They're essentially very small volumes of semiconductor material where all the dimensions are comparable to or smaller than the Brownian wavelength. All right. So in the structures that I showed, all right, you're growing these by molecular beam epitaxy. Okay. So when you're growing quantum wells, you're just modulating the composition and it remains planar. You can also engineer the growth process such that if you deposit just pure indium arsenide, right, then it'll form clusters, right, or islands, rather than a planar film. And then if you bury those, right, that looks like a quantum dot. Right? So that's essentially what what those structures are. And we incorporated those because it gives you a little more flexibility in terms of the critical thicknesses and so forth for a given extension of the range of wavelengths that are absorbed. But because the dots are, ideally pure indium arsenide or certainly indium rich, the potential wells are very deep. So then you have to think very carefully about whether they're so deep that you'll never get the carriers out. Okay, and then the positioning of the dots within the quantum well, whether it's in the middle or at an edge, ends up making a difference as well on whether you can extract the carriers. So there are all sorts of issues like that you have to think about as well. But the basic idea is that you have these small islands that you embed of indium-rich material that you embed within the quantum well that allow you to absorb longer wavelengths.
Thank you.
Any more questions? So let's thank Ed again for and the next one is at 3 p.m. So.